All right, hello everyone. We're looking at our next topic in our part about circles. We've already looked at two types of angles in circles, the central angle and the inscribed angle. We're going to be adding to that today to see what kind of angles we get when we bring in special types of lines to our circles. So one of our first special types of lines is called a tangent line. And specifically, a tangent line is a line that passes through a circle at one point and at exactly one point. So imagine we have the circle here, and I have a point of intersection with that circle and a line. So that would be considered my tangent line. Now that point of intersection has a specific name when it comes to tangent lines, and that is known as your point of tangency. Okay, we call that point a point of tangency for our circles. Now, our other special type of line that we have in our circles is called the secant line. And this one says a secant line is a line that passes through a circle at 2 points. So with that same idea, if I have my circle, the tangent line will pass through it the secant line will pass through it twice. Now there is a special bit of information about this secant line, and that is the fact that this section inside the circle is what we know as the chord. Okay, and that is the part that is inside your circle. Because remember, a chord is a segment, and a segment is a part of a line. So the piece of that secant that goes inside the circle, that is where we get our chord from. Now, when we start merging and intersecting a tangent line with different chords, we get what's called the tangent to a chord theorem. And this specific theorem says if a tangent and a chord intersect at a point on the circle's edge, then the measure of each angle formed is 1/2 the measure of its intercepted arc. So very much like an inscribed angle that had its vertex on the edge of your circle made from two chords for the sides, it's a similar rules here. You're still looking at an angle with a vertex on the edge. So almost like an inscribed angle. But when I'm looking at these different angle measures, what's important to these and what the pieces of the circle mean is that whatever is inside that angle, that is the arc that I have to use that has a relationship to that angle we have. And the same thing is true on the other side of that chord, making the major arc BCA. Angle 2 here, again, is going to have a relationship with the arc that is inside that angle, or the section of the circle that is inside that angle. So we have to be careful and make sure we know which piece am I working with, which angle corresponds to the different arcs. And we have two very similar formulas that we've already worked with. One of those says if I need the arc measure, then I should be able to do 2 times my angle. Same as the formula we saw for an inscribed angle. And then if I need an angle, then I should be able to take my arc and divide by 2. Again, very much like the inscribed. So with those two formulas in mind, let's check out our first example here and see what we have. So we need to find X or Y. And in this picture, we have an X. So what I have to figure out is I need the arc that is inside this angle that corresponds to that piece. And that happens to be this arc that's at the top for 228. So that's the angle I have to use. I'm sorry, that is the arc I have to use to get to this angle. So my formula says the angle should be the arc measure divided by 2. Well, my angle is an x, my arc is 228, and I need to divide that by 2. So that means my x is going to have to be 114 degrees. So that angle, 114. Let's try letter B. This time we are looking for the y, which happens to be an arc of the circle. So that means I need to find the angle that's cutting out that section of arc. So follow that chord down. That is my angle 118. That's the angle I have. So if I need the arc, my formula says it should be 2 times whatever my angle is. So my arc is the y. So I need to know what is 2 times 118. So that means y will equal 236 degrees. So that is a pretty big major arc going on. All right, let's try 2 more for these intersecting on the edge. All right, so sorry, I apologize. There is one little typo that says the measure of arc RT. I want to find the measure of angle 3. I apologize for my typo. All right, so again, angle 3 down in this section of my angle. And again, I have to use the part of the circle matching that area. It's got to be inside that angle measure, which means I have to use 220-degree arc to get to angle 3. So if I need the measure of angle 3, formula says take your arc and divide by 2. So 220 divided by 2. So the measure of angle 3 would have to be 110 degrees. All right, let's try our last one for intersecting on the edge. And we'll look at 2 ways we could actually go about solving this one. So first off, we need angle 6. That's the goal that I'm trying to get to. So I know if I'm going to do angle 6, I need this whole section of my circle, and I need the arc involved. Well, problem is there is not a number here for me to work with. The only number I have is the 160, which is on the other side of the angle. But I do know that these 2 sections, these 2 arcs together, make my full circle. Well, we know a full circle has to make 360 degrees. Well, out of 360, 160 of that is to the left side. So I'm going to subtract that 160 away, which gives me 200 for my missing section of circle. And now I have an arc that I can cut in half. So the measure of angle 6 would be my 200 divided by 2, which gives me 100 degrees. Now, again, there is another way we can go about this. If I extend out my tangent line, well, angle 6 and this empty corner are a linear pair and would have to make 180 degrees. And so very much like the previous one, if I take that 160 and divide by 2, that would give me 80 in here for that missing angle. And then my 80 degrees and my angle 6 are a linear pair. And then I could do 180 minus 80, and I get the same 100 degrees. So it just depends on which way do you happen to see first. But again, there are in fact 2 ways that we can solve this. Now, we've worked on, again, when our circles intersect on the circle, or otherwise known as they intersect on the edge. And we found that in order to use our formulas for these, I have to have the section of the circle that is inside the angle. Okay, so I would have to use this section. I have no choice. When our angles move away from intersecting on the edge of the circle, I get other relationships involved here, and we're going to take a look at those now. So next we have when your angles intersect inside the circle. So my point of intersection inside our circle here. And so my two lines again cross inside there. Now, like we said before, when we were on the edge, we have to use the section of the circle inside our angles. Problem is, I actually now have 4 angles inside this circle. This is where vertical angles are going to come in. Because I know if they are across from each other, my angles on one intersection, then those 2 angles will have to be congruent. So when I'm looking at this, for this picture, the left and right angle, they are vertical angles, which means there's a relationship between those vertical angles and the sections of the circle they cut out. Same is true for top and bottom. The top and bottom sections here are also vertical angles and have a relationship as well with their sections of the circle. So it really depends on which angle are we looking for, because that helps me to match up the different arc pieces that I need. But again, this top and bottom, because of those top and bottom vertical angles, will have a relationship, but they are again crossing inside the circle. Outside the circle is a little bit easier to see, just like it was when it was on the edge. So now we are outside. There is my point of intersection. There's my 2 lines here. And similar to when we're on the edge, I have to use the part of the circle that is inside that angle we are working with. So in this case, there's 2 little arcs that are inside there that I have to use. So let's try with this, these new types of intersections, inside and outside, and see what relationships we have. So we're going to start with our first one that says secants intersecting inside the circle. Now remember, the theorem itself deals with chords, but a chord is part of a secant. So if 2 chords intersect inside the circle, okay, then the measure of each angle is 1/2. There's that divide by 2 again. 1/2 the sum. This is the big difference. Because we had 2 arcs involved when we were inside, we now have to use both of those arcs because of those vertical angles. So it is now the sum of the measures of those intercepted arcs. So for example, if I'm looking at angle 1 is in the right corner. Left is the opposite of right, so therefore angle 1 will also match up to the angle in the left corner. So those 2 arcs that are inside angle 1 are going to have to be used. So arc DC and arc AB. Now, when we get ready to do the formula, it's going to be a little bit easier to use if we don't think about these so much as arc DC and arc AB, because your letters could change in the circle. But we can think about these as a bigger arc and a smaller arc. Your smaller arc will always be closer to the intersection. Your bigger arc always farther away. And I can use a big arc and a small arc in my formulas, because that is always going to happen when your lines, secant lines, intersect inside. You will always have a bigger one, always have a smaller one, because they don't become equal until that intersection is at the center. And then you get central angles. So now looking at angle 2. Angle 2 is the bottom section. Opposite of bottom is the top. So those 2 angles will both have the same measure. And again, that means I have to use those sections of the circles that match up to those angles. They have to correspond with each other. So if I'm looking at the top and bottom angle, then I need to look at the top and bottom sections of my circle. And like before, I'm still going to have a bigger arc that's farther away from my intersection and a smaller one that is closer. So with that in mind, we look at our formulas based off that theorem. So it says the measure of each angle. Okay, so the measure of each angle, angle 1 or 2, doesn't matter, is half of the sum of the arcs, meaning add together your two arcs, big arc plus small arc, and divide by 2. That's what it means by half the measure of the sum of the arcs. Now, if we were going to solve for one of your arcs, there is another version of this that we can use that very much relates to the inscribed angle one. If I need to find that inscribed, if I have that inscribed angle and I need one of my arcs, then I can do 2 times my angle measure, which would equal my big arc plus the small one. And again, we can use that one to solve for one of your arcs. Okay, we can use that bottom version when we're trying to solve for either the big arc or the small one. Now let's add to that. Now let's say we have a secant, that 2 secants are that intersect outside the circle. Now, in reality, it's going to be more than just 2 secants. There are other combinations that we can do here. We can have a tangent and a secant. I could have maybe 2 tangents, or I could have 2 secants. Regardless of which combination, what matters is, do they intersect on the outside? That's what's important. Because when they do, when they intersect on the outside, regardless of the combination, the rules are still the same. It is still 1/2, but this time it is half of the difference. So it doesn't matter which combination of lines we have. If the lines intersect outside, it is now half of the difference. So let's start with our first picture, picture 1 here. Again, the angle I need outside of my circle where my 2 lines intersected. And I have to use the sections of the circles that are inside those angles, or inside those lines, in this case, inside the tangent and secant line. And like before, like with the previous one, we have a bigger arc and a smaller arc inside this angle. So my bigger arc, like the other, is farther away. My smaller arc, closer than the other one. But again, still a big arc and a small arc. Same is true when we come to 2 tangents. All right, for my 2 tangents here, my angle, angle 2 or picture 2. I have 2 points of tangency here, and the sections of the circle that are inside are what I have to use when I am finding my relationships. This time, if you notice, the entire circle is inside your 2 tangent lines. Okay, so that means I'm going to have to use the entire thing. But let's find your arcs. So 1 point of tangency is at P. Well, from PQ over to R, over to my other point of tangency R, there's my bigger arc. And same thing starting from point P and going around to R. There is my small one. Because again, R is a point of tangency. So there's my small arc. So even if we're using the whole circle, I still get a big arc, which is a major arc, and a smaller one, a minor. Now the last one, 2 secants. So my angle is angle 3, which is still intersecting outside. The only part of the circle I can use has to be inside there. So that is this whole space. And again, I will have a big arc, arc XY. Doesn't necessarily mean it's a major, it's just bigger, it is farther away. And I'll still have a small arc, which will be closer to your angle. Now, the formulas are very, very similar to the previous ones when they cross inside. They're almost exactly the same. One difference though. So our theorem says if I need the angle, it is 1/2 of the difference. So that means in this case, my big arc minus the small one, all over 2. And just like we had a formula on the last one that can help us solve for one of these arcs, I can have the same thing here. So if I do 2 times whatever my angle is, that will give me my big arc plus the, minus the small one. And again, I don't use this bottom one unless I'm trying to solve for one of my arcs. Okay, that bottom one we can use if we're trying to solve for one of the arcs. So let's try our bottom examples here and see how we get to use those formulas. All right, so number 1 says we are looking for the value of X. All right, so here is X in the right section of my circle, or the right intersection here. Well, opposite of right is the left, so I also get an X across from that. And so now I know what parts of my circle I have to look at, because they have to correspond to where those X's are. So that means I have a 63 and the arc of 89. And again, I know 89 is bigger than 63, so it will be my bigger one, 63 the small. All right, so my formula says to get the angle, it is the big arc plus the small one. All over 2. So my angle is an X. My big arc is 89. My small one was 63. Add those together and divide by 2. So that makes my X 76 degrees. 76 degrees. All right, let's try another. Letter B. Find the value of Y. So I need to locate that Y first. So it's at the top arc of the circle. So I'm going to use one of those arc formulas to solve. Now, problem is, if I look at the section of circle, the arc Y, I do not have an angle measure that relates to that. There's no number there. Opposite of top is the bottom. I do have an arc measure on the bottom. But again, I don't have either angle that matches to those arcs. What I do have though is a neighbor. I have a neighboring angle here. So what we know about neighbors, they make linear pairs. So this empty angle that I don't have, and 102 is a linear pair, neighbors, they make that secant line. So I should be able to take my total of 180 for a line minus that 102, and I have 78. There's my missing angle measure. So now if I have 78 in the bottom section, I get it at the top. Now I have that angle there. And we can now solve for this arc. So our formula says we're going to do 2 times the angle. Should be the big arc plus the small one because we're inside. So 2 times that 78. My big arc, 95 looks bigger, so and it's farther away, so I'm going to say 95 plus my y. So again, I'm treating 95 as the big, y as the small. Now, if you are visually not sure which is which, it is not going to affect for this one, which one you label big or small. Because when you add them up, you get the same answer either way. Just like 3 plus 2 is the same as 2 plus 3. You could reverse the order, you still get 5, whichever way you do it. So for addition, it does not matter which one is necessarily the big or the small if you're not sure which is which. So 2 times 78 gives me 156 equals 95 plus y. Now we can solve these out. Subtract the 95 from both sides. And my y is equal to 61 degrees. All right, 2 to go. Now with our last example 4, we're going to be looking at your angles that intersect outside of the circle. So remember, it does not matter what combination of lines. What matters is, do they cross inside, outside, or on the edge? And this one crosses outside. There's my angle X. So the only things I can use in the formula have to come from inside that angle. So I have a 78 and a 42. There is my big arc, 78. And my little arc, 42. So my small. So the formula says to get that angle, I should be able to subtract these, the big one minus the small one, over 2. Well, 78 minus 42 gives me 36. And when I cut that in half, I get 18 degrees. So again, anything outside of that angle we cannot use. All right, letter B, we've got another solve. We have our angle down in this bottom corner. When I draw my lines on out, then I can see where my sections of circle are. They have to be everything inside that angle. So we've got an A and a 44. So now we need to decide which piece is the bigger one, which one is the smaller one. And remember, bigger is always farther away. So my A will have to be the big. My 44 will be the small. And I've already got my angle. So let's plug in everything we know. So same formula as before. 2 times our angle of 30 is our big arc, which is an A, minus the small one, 44. And now we can solve this out. 2 times 30 is a 60, which should be A minus 44. Add your 44 back. Sorry, that did not look like a 44. And I have 104 degrees for angle A. Or arc A, I apologize, arc A. All right, guys, so I hope you enjoyed learning a little bit about your secant and tangent lines and the angles they create inside your circles. Please don't hesitate to reach out to me if you have any questions at all. Bye, guys.